Good afternoon, everyone. My name is Mo. I'm a co-founder of Brevis. Today, I'm going to talk about what we have been building a smart ZK coprocessor. You may not know the concept here, but after the talk, hopefully you can know why we're building this and why this makes sense. So blockchain has evolved a lot since the first introduction of Ethereum. We have the layer 2s, alternative layer 1s, many different blockchain stacks. And they're all great, but the problem is that they are all still based on distributed consensus, and therefore, they're still fundamentally bad at data-rich and very heavy computation. Right? So this is kind of the natural nature of blockchain, because even though we have so many different innovations and evolutions based on blockchain architecture, their VM construct is still very much similar. In the end of the day, they're still relying on a distributed consensus across multiple nodes. So, what's the problem, right? Well, it means that for certain type of computation, blockchains are just fundamentally bad to do. Let me give a very simple example: a trader, VIP trader web. So on every centralized exchange, you always see this type of fee-based, trading volume-based fee tiers. Basically, in the previous month, for example, if you traded more than 30 million, next month you will get like 50% fee discount. On every centralized exchanges, you see that, right? So like Coinbase, Binance, you have all of these exchanges have that. But if you look at any of the decentralized exchanges, none of the decentralized exchanges actually has that kind of a capability to do this type of trading discount. Why is that? Well, turns out that to do this type of calculation on blockchain, because smart contract doesn't have the capability to easily do this type of historical data access and computation, you actually need to cost like basically 4 hours of full blockchain time and maybe 60K in just the fees to actually do this type of computation for just one user. So this is why we're not seeing any of the user experience differentiation, user experience segmentation based on user value, any type of data-driven thing, computation, you don't see any of that in smart contract because there's no way to do that today. The reason for that is that, in theory, you can do that on blockchain directly. But how you will do that is that you basically need to look back and find what are some of the block headers for the data you want to access and expand that, right? So like block header is basically a very succinct compression of all the blockchain data. You sort of have to expand that by rehashing all these nodes back to the blockchain header on-chain in smart contract directly, and that is super expensive. So what you're going to have to do is doing all of this, and therefore, what the result of this is that blockchain as a compute construct doesn't really have a trust-free access to historical on-chain data, right? So even though we are using blockchain, every single piece of data, every event, every swap, every transaction was recorded on blockchain. But a smart contract only have very limited visibility. It only have the visibility to now the current state of the entire virtual machine, but there's no visibility in the past. And of course, there's no trust-free data access to other blockchains for similar reason, and just generally bad at data-driven and very complex computation. How do we solve that? Luckily, we had this type of problem before in computer history. So when we introduced CPU was evolving and everything is kind of doubling in terms of the speed. But CPU as a computer construct is still very bad at certain type of computation. Things like parallel computation, things like drawing triangles, basically. This was why we introduced a CPU coprocessor to handle something that CPU are generally kind of a bad at. That coprocessor is now known as GPU. The introduction of GPU as a coprocessor is how we have now AI, amazing graphics of gaming and all the amazing CGI effect of kind of a favorite movie today. So blockchain as the Web3 CPU also needs its own coprocessor to offload certain type of computation tasks that is hard to do, while let the blockchain itself just focus on transactional computation, and let this coprocessor to handle all the data-rich and very complex computation, and return the result back to the blockchain for the smart contract to use these computation results. But the most important thing here is that we need to make sure that this whole round trip here needs to be maintained in a trust-free it needs to maintain a trust-free nature for the blockchain computation itself, meaning that even though the computation itself is happening off-chain, we should not introduce any additional trust assumption to any third party except for the blockchain itself. So how do we do that? Well, we use zero-knowledge proof to do that. And we introduce Brevis as a ZK coprocessor to achieve that goal. What Brevis is a ZK coprocessor that can generate zero-knowledge proof off-chain for arbitrary data type and for arbitrary computation on any data. And you can actually submit that proof back to the blockchain, feed that into your smart contract, and allow your smart contract to actually use that data in an entirely trustworthy way. There's no trust other than trusting the blockchain consensus itself. So using Brevis is actually very, very easy. So you just have 3 steps to actually use that in your smart contract. The first is that you just need to specify what type of data you want to read in your smart contract. It can be storage state that include things like NFT, ownership, token balances, and so many things that is like just a variable in your smart contract. And then you have block information like block headers, what is beacon chain state, and receipt, transaction receipt, which are events. These are very important because like things like swap event, are included in that, and transactions and accounts in all the supported blockchains. And you can specify that very easily in SDK without actually requiring to understanding and without actually understanding anything about DK. And then you do computation on top, right? So like we actually provide a very, very high level and clean abstraction of data streams where you can do map reduce, group by, filter, all type of data computation based on the data you gather and calculate the computation result you want. And finally, you can submit the computation back alongside the ZK proof. Note that, like, the key thing to note here is that it's not only the computation itself is a zero-knowledge proof, but also the data associated with that. Basically, we're proving 2 things here. One is that the data used in the computation actually existed in the history of blockchain. And second, the computation itself is actually correct. And you can feed the data back to the blockchain. So going back to the example I just talked about, when we talk about ZK, the biggest question we always ask is like, is it feasible, right? So what is the scalability? Well, I'm very happy to say that this is like actually very, very feasible to use in production, because for example, to generate a trading volume proof for 1,000 transactions on Uniswap V3, right now just costs $1.8. And what that means is that you can generate for Uniswap, the total volume, the total number of trades on a monthly basis is just 4 million trades. And on an 8-server machine, Brevis now can generate like 19 million transaction capacity at the cost of about $7,000 per month, which is like just a tiny fraction of Uniswap fee. So it basically shows that as a ZK coprocessor, it has the capability to do large-scale proof and also have the capability to handle production use cases. Now, of course, ZK itself is still relatively higher cost. So this is why we also introduced a new construct called Brevis Coaching, which is an eigenlayer ABS that allows that enables the combination of the crypto economic security and ZK proof security. So conceptually, how this works is that instead of always generate the ZK proof upfront, you can have a co-processing request submitted to this ABS, and let this ABS generate the result first for you as a proposal that is secured by the crypto economic security. The crypto economic secure validated result will be submitted on chain, and at the same time, a challenge window will be open. And during that challenge window, if there are challengers who realize that the result is incorrect, he can actually start a challenge and submit at a later stage a ZK proof to show that, okay, this result you generated this via the ABS crypto economic security is actually incorrect, and therefore getting all the kind of malicious validators or malicious node operators slashed for their stake. So this type of combination, obviously, in most of the cases, will significantly reduce the cost of ZK coprocessing because in most of the cases, you actually don't need to generate the ZK proof upfront. But most importantly, it also enables very important features for things like proof of completeness and proof of non-existence. For example, if you want to generate a proof that like a user have never interacted with a certain smart contract, in pure ZK mode, it's very hard to do that because you need to generate a proof for the entire blockchain history. But in this kind of a crypto-economic plus ZK model, this becomes very easy because in the crypto-economic security model, you just need to submit a proposal saying that, hey, I can claim that there is no such transaction or there is no such interaction. To challenge that proposal, you just need to prove one existence of a transaction, and therefore it is much more powerful than just like a pure ZK model itself. So there are many different kind of use cases that you can use this type of ZK coprocessing for, because now you can think of your smart contract has access to things like a dual analytics dashboard, right? So like it has many data insights that it can use in the smart contract logic directly. One of the biggest category that I want to kind of explain a bit more on is data-driven DeFi. So in DeFi protocol, you have all these type of events: LP deposit, swap, liquidation, Oracle price feed, and you can actually take all of these historical events and data and do whatever calculation you want, and use that calculation result to drive your protocol parameter in a dynamic way. An example that I just mentioned is Uniswap's dynamic protocol feed configuration, but there are many other use cases such as trust-free active liquidity management. Things like you can actually basically allow a liquidity manager contract to manage and move your liquidity around between different protocols, rebalance your liquidity based on certain on-chain conditions, saying that, for example, if on-chain price actually moved to a certain point, and then this is a criteria for rebalance of the liquidity. How do you do that today is that you actually need to rely on you basically need to trust the active liquidity manager. But with Brevis, you can do this entirely trust-free because the active liquidity manager can prove on-chain that this price actually already moved, on blockchain directly. So another very interesting use case we're seeing is something called retrospective farming, reward based on LP contribution. Today, if you look at some of the DEX's farming reward distribution, it is entirely based on time. You deposit your liquidity in, and you get reward immediately. But this is actually very, this is actually not optimal because the timelines of in many cases, what we saw is that when the volatility of the market comes, many of the LP will just withdraw their liquidity and without kind of getting others selected in the market. So what happens is that you are distributing vast majority of your liquidity or farming reward to these LPs who are not actually providing liquidity service or who are not actually providing trading desks for your desks. Instead, what you should do is by looking back and looking into the history and see which are the LPs that are actually contributing to the protocol by looking at the actual fee generated by each of the LP position and distribute the reward based on that. So this is like a very powerful primitive that is not available in any of the DEXs today, but we're building with some of the biggest DEXs now. And there are other things like trust-free temporal intent-based automation. Things like intent-based frameworks that are focused right now on just one point in time. Like right now, I want to do something. Let's find the solver and do that for me, right? But like we can actually extend the scope of intent-based framework using Brevis by generalize the condition into future conditions, right? So like now I can specify saying that okay, I want to do something when this condition is actually met. And using Brevis, you can actually prove on chain that certain condition is actually met using kind of a ZK proof that's generated by Brevis. So there are so many different use cases, such as ZK reputation, where you can basically have a reputation score generated based on your on-chain behavior and clustering algorithms, and UX personalization that focuses more on a per user basis by differentiating user experience across your user group in a single application. Right? If you think about right now, every user in every DEX is experiencing exactly the same thing. This is hardly the case for Web2 application, and you can do this kind of user experience differentiation and UX segmentation based on their actual on-chain interaction history before in an entirely trust-free way. There are many different other use cases you can do with Brevis, but what we want to highlight here is that Brevis is a new thing that can enable your smart contract to see more and do a lot more. So with that, happy to conclude my talk in the forum.
Thank you, Mo. Thank you very much.